I'm sure, as kids, we have all desperately tried to fit that triangle into the circle. It just doesn't fit, right? Now, imagine redesigning those cavities so that the shape is not a circle, not a square, nor a triangle, but your targeted molecule. And that is exactly what we, HelvetSens, have devised to capture VPA. This technology, known as molecular imprinting, is achieved by mixing specific monomers with the molecule of interest, resulting in the formation of a stable complex, which is fixed through electropolymerization. The target here serves as a template so that the polymer solidifies around it, allowing, once the template is removed, to leave behind cavities perfectly tailored to its shape. The monomers are functional groups which provide complementary interactions, increasing thus the affinity of the cavity. In our case, monomers were chosen to mimic the natural binding site of VPA. The alpha-cyclodextrins provides a guest host interaction between its hydrophobic group and the aliphatic chains of VPA, while the carboxylic group of VPA will form an electrostatic bond with the NH2 groups of acrylamide. We use this technology for electrochemical sensing. We mix the monomers, template, as well as gold nanoparticles to enhance the electron transfer and perform the electropolymerization onto an electrode. After an elution step, our polymer has cavities perfectly matching the shape of VPA. If VPA is present, it will bind to the monomers in the cavity. We will then be able to measure a current. But to do so, we need an electroactive probe, which will, in proximity to the electrode, generate a current that we are able to measure. We chose ferrocyanide.
Why ferrocyanide? Besides being electroactive, its rather small size allows it to penetrate the binding sites of cyclodextrins with neat cavities, which makes it a great competitor of VPA. But those cavities have been specifically designed for VPA, which still exhibits a higher affinity for them, and that greatly reduces ferrocyanide binding to cyclodextrin. Essentially, the more VPA we have in our sample, the less ferrocyanide and consequently the less current is generated by the electrode. Hence, we obtain an indirect measurement of VPA concentration by measuring the different current peaks of ferrocyanide oxidation. To measure the current, we use differential pulse voltammetry, which consists in applying short increasing steps of voltage pulses and measuring the resulting current. The current difference at each voltage increment is plotted as a function of potential. A complex sensor to use, you may think. In reality, all of this happens in a black box. Yes, I mean a real black box. The user simply collects 20 microliters of serum using commercially available micropipettes and deposits it in the reservoir located at the electrode and preloaded with 30 microliters of ferrocyanide. Our electrode is connected to a potentiostat and records the output current, which is converted to a concentration. The value is displayed on the interface and sent via our Wi-Fi module to the user app, which will keep track of past measurements and statistics. Our device presents many advantages. It's fast, small and portable, while offering high stability compared to other recognition species such as antibodies. Our device also allows to measure free VPA directly and can be extended to other molecules. Thank you for your attention.